Hello everyone. In this video, I'll talk about how do lasers work. I will explain the science behind them. I'll go through Einstein coefficient, what's absorption, spontaneous, and stimulated emission. And I'll talk about the laser cavity and how do the mirrors work and how light actually amplifies using those mirrors. Let's go ahead and get started. Before going deeper into science, you really need to first know what the laser stands for. The laser stands for light amplification by stimulated emission of radiation. So there is some kind of amplification by some kind of stimulated emission of radiation. The radiation is basically the light, the incoming source. So somehow they get amplified, and that's what the laser generates. The main difference between lasers and the normal bulb is its coherency. It's a unidirectionality, it's wavelengths. So the normal light, like what we have in our houses, and then I'm going to draw a laser. So it's like kind of laser pointer where the teachers use. So in a normal light, so I will just say this is just a bulb, and then this is laser. The normal light spreads the energy, the light, in all different random direction. So it has a different wavelengths, and then different direction, different coherency. So there is no any similarity between those among those wavelengths, among those single light sources that was generated by bulb. But in contrast, the lasers work a little differently. For lasers, it's all the same wavelengths, same direction, same coherency. Everything is identical. That's why when you point the laser, like it generates the red light typically, that's why you can see it's traveling across that certain distance, and then it's hitting the wall, and then you can see it's like very, very focused. That's why they're very coherent. And then today we're going to talk about how exactly we can make a normal light, we can turn it into the laser. So in 1917, Albert Einstein proposed the mechanism of the laser. So he explained three fundamental mechanism of the lasers and how they work. So let's go ahead and get started. The first one is the absorption. The second is spontaneous emission, and then the third one is stimulated emission. So let's go through them one by one. This is very important. So in absorption, you may probably know we have two states. You probably have seen that on Jablonski diagram. If you went through any spectroscopy instrument like a UV or fluorescence. So we have here a ground state, and then we also have an excited state. So S1. So S0 is a ground state, and S1 is an excited state. So what happens when we have a typical molecules or atoms? They stay stable. They are typically on the ground state. So I'm just going to write one molecule here. It's just a molecule. It's on the ground state. It's stable. So what happens when we apply an energy? In our case, it's a radiation, which is the typically light source, incident light. We apply the light, and if the wavelengths really matches the energy between S0 and S1, so what can do it? It will excite that molecule from the ground state to the excited state. So it promotes from ground state to excited state. So as a result, what happens is molecule jump from here, from S0, and then land right here in S1. and FOI, not any energy, but the energy should match between this S0 and S1. So you've probably seen that on when you go through the IR or other type of spectroscopy. It's just a normal excitation. And then what happens is the molecule doesn't stay there for long. The molecule tries to get back to its stable, more like a secure, more safe place, back where it was. So after some time, this molecule or atom will drop back to the ground state. So as you remember, it absorbed the energy and went from lower state to the excited states. And now, after some time, it will come back from higher state, the excited state, to the ground state, and it releases back the energy. It doesn't keep that energy. And in our case, it's a light. If it absorbs the light, and then it releases right back. So that's what we call an emission. And in our case, in a spontaneous emission, what Einstein says, in spontaneous emission, it's just randomly releases that energy. That energy does not match, does not have any similarity with the incoming photon, with the incoming energy or incoming light. So again, so this one was absorption. Apologize, it should be absorption. And then the second one is spontaneous emission. Spontaneous emission. So again, according to spontaneous emission, the molecule just randomly goes from excited state to the ground state, randomly generating or releasing back the energy, or in our case, it's a light. So it's a one photon in and then one photon out. This is spontaneous emission. You've probably seen this in fluorescence spectroscopy. Under fluorescence spectroscopy, light absorbs and then light will be released, and then that's why you can see those the molecules shining on the microscope, because that's due to the emission. So another name of fluorescence is emission spectroscopy. So there is no any lasing yet, so this is just a normal procedure. So now the third mechanism what we're talking about is stimulated emission. And that stimulated emission actually very important during lasing. And that's the core, the main idea behind the lasing. So according to stimulated emission, unlike spontaneous, so what happens is when the molecule is on the excited state, so we apply more energy, we apply a little more light there. When we do that, when we apply the light, that light is gonna interact with the atom or molecule on the excited state and force that to generate a second photon. So now, in spontaneous emission, as I said, one photon in, one photon out. But in stimulated emission, one photon in, two photons out. So it generated a second photon. So who cares? So what's that second photon? Why it's important? The important part is that second photon has exactly same wavelengths, coherency, directionality of that incoming photon. So it basically generates its own twin. So that's how emission, that's how the stimulated emission work. So I'm just gonna write here, stimulated emission. Okay, so stimulated emission. So the molecule, of course, then eventually, or atom, comes back to ground state. But now it's going to be one photon in, two photon out. And these two photons, they're identical. Same. The key point here is same wavelengths, unidirectional, and coherent. That's what makes the laser very, very special and important. So that's how it works. So the next thing is, all right, so then how can we actually practically generate this? How exactly we can practically generate those laser sources, or just like the pointers that I just talked about? Because this is just the mechanism which was proposed by Albert Einstein. So before going to the practical explanation of lasers, we really need to understand one small detail. There is a requirement to perform the stimulated emission, and that requirement is called population inversion. According to population inversion, the more molecules or atoms should be on the excited state. So we have here ground state and an excited state. So we have way more atoms on the excited state in comparison with the ground state. So that makes sense because, as I mentioned it, the stimulated emission occurs only when the incoming, when the photon or the light is going to interact with the molecule which is already on the excited state. So that's why we have to make sure we have enough number of atoms on the excited state so that the photon could interact with them. Without then, there wouldn't be anything a photon could interact with. So that's why it's very highly required to have a population inversion during a stimulated emission. So I'm just going to write this as population inversion. All right, so what is next? So next is, so now we have to make sure we have to build that laser practically. How do we achieve that? How can we achieve this, the stimulated emission? Because I just explained it more like theoretically. So how can we practically use that? So what we have here is, what scientists build is some kind of medium. We have a medium typically made of the gas or liquid inside. So what they do is, the medium has a mirrors on each side. On the one side, there is a mirror. Sorry, I'm just going to draw it properly. So this is mirror number 1, and this is mirror number 2. So mirror number 1 is it's 100% reflective, or it's fully reflective. So I'm just going to write it's fully reflective. This is mirror 1. And then mirror 2 is partially reflective. Partially reflective. Okay, so it's a gain medium, and then there's 2 mirrors. One is fully reflective and one is partially reflective. So what happens is this spontaneous and stimulated emission is occurring right here. So we built the emission system right here, the spontaneous and stimulated emission. So well, how can we generate a laser? Because it's just one. In order to generate a beam, we need like hundreds, thousands, millions, billions of lights that should be generated. So here now, I'm just going to erase this because it's destructive. So here we have a emission going on right here, right here, or right here. So when molecule interacts with the light under the stimulated emission I just said, it's going to generate a second photon. But we need to make sure that the photon, the same photon with the same wavelengths, should interact with that molecule on the excited state. Not just an incident light, but the photon with the same wavelengths. So here, when the emission occurs, as I mentioned, according to spontaneous, it may generate anywhere. So it was here, 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 anywhere it's generating. So what we care about, the light that has been generated along the axis of the medium, along the axis, this light. So this light, which was generated by exciting the molecule, should travel along the axis of medium, and then the rest, they just randomly disappear. So but the only one that keeps along the axis is they travel towards the mirror, they hit the mirror, and then come back, because no, it's a reflective mirror, and then come back and then interact with that molecule a second time. Interact with that molecule which is on the excited state back, because it goes and then the molecule generates the photon goes and then hits the mirror and then comes back, interacts with the excited molecule a second time, generating a second photon. That's how stimulated emission work. And then but the remaining the light that has been generated, they just randomly they just disappear, and only light that can hit the travel across on the direction of along the axis of the medium will be preserved inside the medium. They start going, hitting the wall, which is mirror, and then coming back, and then exciting the molecule, which is already excited, forcing them to release the second photon, goes back to the other direction along the axis and hits the mirror, the other mirror, partially reflected mirror again, and then comes back and then stimulates again, generates the second photon, or in our case, a third photon. 3 photons goes and then comes back, stimulates again, generates 4, goes the other direction, comes back, stimulates another emission, another photon. So that's how photons are exponentially amplifying. Going back again. So here is the photon coming back, and then this photon goes the direction, and then hitting back, and then comes back, and again, and here actually there are 3 photons, and then all 3 photons then comes back and then stimulates another emission, and then now it becomes 4 photons instead of 3, and then all 4 photons will go back. So, and this is how quickly medium gets saturated. It reaches its threshold. The photons are jumping back and forth along the axis and then keep stimulating the emission, another photon, generating a second photon. It exponentially grows. And then once it grows, once it reaches the threshold, then it's using this partially reflective mirror is going to release this photon beam more coherently, release that beam. That's why when you hit that laser, the pointer, it's going to release that the photon, the light, the red light, the pointing. That's why you point it on the whiteboard or anywhere. So as soon as you hit, within a millisecond, within a microsecond, it's going to quickly reach the threshold of the medium, and then it releases the photon. So that's how the lasers work. So it's very, very important here to have 2 mirrors that one is fully reflective and one is partially reflective. And again, we have to have some kind of stimulation, that emission, to generate those lasers. So that's why what we are doing is the light amplification. We're amplifying the light by stimulated emission. Here's the stimulated emission, which is going inside this, of radiation. And radiation is just an electromagnetic wave, which is a combination of electric and magnetic wave, which is simply saying a light. So light is being amplified by stimulated emission. So this is how lasers work, and many current instruments like fluorescence, Raman,
And many more, the UV, many more spectroscopic instruments, they have a laser as a source, and that laser will help them then to excite the molecule to the excited states, and then they can perform those spectroscopic analysis. So instead of like a normal light, which goes in all directions, that can spread, now we can use the laser light, which is coherent, unidirectional, and monochromatic.